Okay, so this video is going to show you how you can use what we know about geometric series to write a power series to help us come up with these infinite polynomials to approximate some rational functions. So we're going to work our way into it. So take a deep breath. So let's remember our geometric series. So remember this, so a plus a times r plus ar squared plus ar cubed, right, on infinitely. And that converges to, right, it has a sum of, if that was your language, a over 1 minus r if, right, as long as the absolute value of r was less than 1, right? As long as that constant ratio was less than 1, then your geometric series would converge and the sum would equal a, that first term, divided by 1 minus that common ratio. Okay? So I just wrote that right, kind of concisely here. So this, right, in the the series notation, so from n equals 0 to infinity of a times r to the n, this equals a over 1 minus r as long as the absolute value of r is less than 1. Okay. So now what we're going to do is we're going to take a step and say, okay, well, what if we toss some x's in to go along with that? Okay, so I'm going to swap out that r, right, and put in an x. So then it would be, right, a plus ax squared, dot, 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 and you can factor out the a. So what that leads to, so now, right, I have 1 plus x squared plus x cubed, dot, dot, dot. So writing that as a summation notation, so n 0 to infinity, a times x to the n, right, what is that going to equal? Right, so it's going to be the same thing as we had for our, right, just making a comparison between this line with a times x to the n and a times r to the n, right? So it equals a comes out 1 over 1 minus x as long as, or for all, this is our symbol, for all x's, absolute value of x's that are less than 1. Okay? So that is super powerful, right? If you, right, if you can write a power series, right, then we can find its sum and we can find this radius and interval of convergence. Okay? All right. So let's see how this could possibly work. So I have this function here, 1 over 1 minus x cubed, right? It's not a bad function, but if I had to do a lot of calculations on it, right, it might be kind of tedious because I've got cubing, I've got a subtraction, and I've got a fraction. So if I could come up with a power series that represents this function, right, then that power series, that infinite polynomial, might be easier for me to deal with. Okay, so let's see how we can compare this function here, right, 1 over 1 minus x cubed, right, to this line I have here. I'll go ahead and put a big old box around it. This is going to be our go-to for right now. Okay, so in this one, I'm given the version on the right, or something similar to what we have on the right, and I want to write it as this power series on the left with the summation. So I'm just going to do a comparison here. So it looks like a is equal to 1, right, because I don't have any other coefficients, so that's nice. But I don't just have an x there, do I? I have x cubed, right? So I'm just going to replace my x with an x cubed, right? So x is going to take the place of x cubed. So writing this, and the minus is still there, so that's great. So the way I would write that, right, as a summation notation is I would say that this function is equivalent to, at least for some values of x, it's going to be equivalent to the summation as n goes from 0 to infinity of 1 times x cubed to the n. Okay. Or, right, the summation of x to the 3n as n goes from 0 to infinity. Okay, so for what values of x is this going to converge? Okay, so again, we're going to scroll. Okay, so this was true whenever right, this part that was right here, right? And if you want, I could have used a U down here that I'm pointing at that you can't see, right? Whenever that x or the u is less than 1, that is our radius of convergence. So I would need my x cubed to be less than 1. Okay, and that's going to be true whenever, right, you can just do the cube root, whenever x is less than 1. And since x can't actually equal 1 because that would cause division by 0, right, so then I know, right, this is my radius of convergence. Right, r equals 1. And my interval of convergence is from -1 to +1, not inclusive. Okay, so before I do the next one, I want to show you something super duper cool. Okay, so this was my function that I started with, right? And it's going to have some graph, and it'll have a domain and a range and all of that. I have come up with this power series. Why don't we call that P of x? N equals 0 to infinity, x to the 3n. And let's just write out a few terms of this power series, right? So P of x, this polynomial, if n is 0, I get 1. If n is 1, I'll get x cubed. If n is 2, 3 times 2 is 6, I'll get x to the 6th, right? X to the 9th. And it would go on forever, okay? So what we have just found is this polynomial, 1 plus x cubed plus x to the 6th plus x to the 9th, approximates that function, 1 over 1 minus x cubed, as long as your x values lie within this interval from -1 to +1. Let me show you what that looks like on the calculator. Okay. So here, let me zoom in. Right? So for my y1, I have the original function, 1 over 1 minus x cubed. And then in my y2, I've put the polynomial out to x to the 9th, right? And you could put more terms if you wanted. Okay. Oh, I don't want a graph. Okay, let's turn these guys on. So my window, I'm fairly short. I'm just -3 to +3 on my x's, right? Because I'm only interested in between plus or minus 1 for my x's. That's my interval of convergence, right? And then the y's, those will be fine. So this blue line, that's the actual function. And now look what happens when that polynomial comes in, right? That red line is tracing right over the top of the blue line between, right, -1 over here to 1, right? Well, it's super close at least. And we could add some more terms onto our polynomial, right, and get it to agree even further out. Okay, cool. Let's do one more of those. Zoom back up. Okay, so we're going to find that power series expansion, just another phrasing for that same thing we just did. And this time our function is 1 over 4 plus x squared. And then we're going to find that radius and interval of convergence as well. Okay, so what is it we're comparing to again? Okay. So that, I'll switch them around. We want to make this look like a over 1 minus x somehow. And then that will be equal to, so the power series version of it is ax to the n, right? Okay, so somehow, right, we need to convert this, right, this function that we have to look like 1 or a over 1 minus x. Okay. Well, right, we can already see we're going to need to have, right, a negative. We're going to need to change the sign. And then I need this 4 to be a 1. So let's start by, let's factor that 4 out of the denominator. So we're just going to do some algebraic manipulations here. Okay, so what do I have? I have 1 over, and I can bring the 4 out. So then it's 1 plus x squared over 4. Okay, well, that's a little bit better. Okay. And now I can let u equal, how about x over 2? Ooh, how about negative x over 2? And then this 1/4, I'm going to let that move up top, so that'll be my A. So now I'm still just manipulating. So now I have 1/4. And on the bottom here, I'm going to have 1 minus, because I need to get rid of that plus, right? I need it to be a minus. 1 minus actually, here, hold on. I think I got so excited because everything was a perfect square. I'm just going to let u equal negative, right, x squared over 4. Have it be the whole thing there, right? So then I have 1 minus u, if u is the negative x squared minus 4. Okay, so I've got it into our pattern, right? So this is the sum part. So how is that going to look as interval notation? I'm sorry, not interval, summation notation. Keep getting distracted here. Okay, so I have my A, 1/4, X, which is right now being played by U, so that's negative x squared over 4 to the n, as n goes from 0 to infinity. Okay, and then we can do some manipulating on this for sure, right? So let's see what that could look like. Because this is totally fine. It might not be what you see, right, in your notes, and you could write out a few terms, see what that's going to look like, or you can just do a little exponent work here. So I'm going to I have an alternating series, so I might do that with our regular alternating series thing. So I'm going to have the negative 1 to the n. Then I have x to the 2n. And then I have this 4, but then I'm also going to have a 4 to the n. So that'll be a 4 to the n plus 1. How about that? N equals 0 to infinity. Okay, so there is our power series expansion written in summation notation. Okay, and now how are we going to find the interval of convergence? Okay, so, and I don't have to go all the way back. I don't have to do the ratio tests, right? Because I already know when my geometric series converges, right? It converges when x, now being played by u, which is negative x squared over 4, it converges when the absolute value of that is less than 1. Okay? So that'll be when, so absolute value of the negative, so I can get rid of the negative. When that is less than 1, multiply your 4. So the radius of convergence is 4. And my interval of convergence, right, negative 4 less than x squared less than 4. Oh gosh, hold on. Radius of convergence isn't 4, it's square root, right? Sorry, you have to square root both sides. There was an x squared in there. Thank you, those of you who are shouting at me. Okay. So negative 2 to 2. Oh, the scribbling instead of the whiteout. Sorry for those of you who that makes crazy. So negative 2 to 2. Okay. For my x's, not my u's. And then, right, we could go back and we could check our endpoints. Should we do that real quick? Okay, I am going to scroll. Right, so here is my series. So let's check those endpoints. So we'll check negative 2 first, in for the x. So checking those endpoints. So does negative 2 let my series converge? So n equals 0 to infinity. I have my alternating term. I have x being replaced with a negative 2 to the 2n over 4 to the n plus 1. So negative 2 squared, that'll be positive 4. to the n, and then it's over 4 to the n plus 1, n equals 0 to infinity. So 4 to the n over 4 to the n plus 1, that is, right, so 4 to the n plus 1 is 4 to the n times 4. Negative 1 to the n, 1 over 4, n equals 0 to infinity. So does this series converge? And it does not, right? This is just 1/4 minus 1/4 plus 1/4 minus 1/4 plus 1/4. Okay, so we won't include the negative 2. Let's see if we include the 2. So that looks like we're going to get to the exact same spot because it'll still be, right, our alternating term, negative 1 to the n. I'm going to get a 4 to the n divided by 4 to the n times 4. Right, that's my 4 to the n plus 1. Negative 1 to the n over 4. Same exact series coming out. So we don't include any of the, either of the endpoints. So our interval of convergence would be negative 2 to 2. So our radius of convergence, 2, not 4. Make sure you got that fixed. And then here is our power series. Should we write out okay, I know I'm going long. Let's write out a few terms of our power series, and then let's do these on the calculator too, okay? So let's write out the first couple of terms of that power series. So let's see, n equals 0. I'm going to get 1, I'm going to get 1, I'm going to get 1/4. N equals 1, so that'll make it minus. I'm going to get x squared over, so n is 1, I'll have 4 to the 5th. I'm sorry, n is 1, started thinking instead of doing. N is 1, I'll get 4 squared. How about that? Yeah, that's better. Okay, n equals 0, n equals 1, n equals 2. So negative 1 squared is positive 1, so it's plus. N is 2, so that'll be x to the 4th. N is 2, 2 plus 1 is 3, 4 cubed. Okay, I can keep writing now. Negative x to the 6th, x to the 4th. Should we do one more? Plus x to the 8th over, oh, for goodness sakes, Angela, 4 to the 4th, 4 to the 5th. Yikes. Okay, calculator. Y equals, clear out what you had. So in y1, right, you're going to put your function. So 1 divide parenthesis 4 plus x squared. And in y2, we're going to put, right, some of these terms of our polynomial. So I'll have 1/4, 1 divided by 4, minus x squared over 16, plus x to the 4th over 4 cubed, minus x to the 6th. I hope you guys are watching this because obviously I keep dropping things. 4 to the 4th. Okay, I don't know that one off the top of my head. Okay, the next one, last one, plus x to the 8th over 4 to the 5th. Okay, so now my interval of convergence is negative 2 to 2, so I'm just going to make sure I've got that, I'm sorry, on my window. Okay, let me show you my y equals in case those were off. Okay, so let's see what we're going to get when we graph this. So the first one will be the function. Oh, I need a better y window. Okay, and here comes our polynomial. Right. Look how close that is. It's going right on top. As long as, right, you stay close to that between negative 2 and 2. Let me change that y the y scale. I'll make it much smaller. How about we'll just go -1 to 1. Okay, here comes the function. And here comes our polynomial, right? It doesn't look good until we get in close there to the -2 to 2. And then it's laying down right on top.